Hello, everyone. This is Masaharu Kobayashi from the University of Tokyo. So it's a great honor to have a presentation in this very nice workshop. Thank you very much. So today I'd like to talk about our recent research progress on the monolithic 3D integration of non-volatile ferroelectric memory and also a transistor on top of the CMOS circuits. So I'm currently doing the research with the GST SciCorp program with the help of Taiwan MOST for 3 years. So in this program, this is me, and in this program we are doing not only advanced research but also building a young researchers collaborative relationship, so which hopefully leads to the future leadership of the Japan and Taiwan in the field of semiconductor area for long term. So I'm working with Dr. Su from TSRI, Dr. Lee from TSRI, and also Professor Hu from the NTU. We have a very good synergy among Japan and Taiwan. So moreover, our university, the University of Tokyo, has an alliance with the TSMC. So we have a very good wide advanced semiconductor technology collaboration. So Japan and Taiwan, we have a more strong relationship for the future leadership of the semiconductor area. Okay, so going back to my talk, today I'd like to talk about our recent research progress. And so especially today, I'd like to talk about the monolithic integration of oxided semiconductor FET and also ferroelectric capacitor on the back end of line layers. So let me briefly introduce, let me have a kind of short introduction of this research. So as you know, AI chip is one of the big technology driver these days. So AI algorithms such as machine learning requires very energy efficient computing for the semiconductor chip. So AI algorithm requires a lot of data transfer between data processing unit and the memory units. And typically, we said that there is a von Neumann bottleneck between processing unit and the data memory. So so these days there are a lot of integration scheme to increase the data bandwidth between processing unit and also embedded memory, especially using the 3D integration technique. So ultimately speaking, to make highest bandwidth between the non-volatile data memory and also a processing unit, we should put the embedded memory directly on top of the processing unit in the back end of line, so that we can transfer the data with a very high bandwidth. But there are several embedded memory technologies these days. However, for example, embedded DRAM requires an access transistor next to the CPU core. So it requires a wider area, and also because of its 2D configuration, the wiring interconnection wiring overhead becomes larger in terms of energy consumption and also propagation delay. So we propose this kind of direct integration of embedded memory directly on top of the CPU processing unit. So in this talk, I talk about 1T, 1C non-volatile memory directly on top of the CPU unit. So to enable such 1T, 1C non-volatile memory integration, we need to have a good back-end compatible transistor technology and also capacitor technology. So in our laboratory, we have been studying two back-end compatible device technologies. One is ferroelectric hafnium oxide, which was mentioned previously. Ferroelectric hafnium oxide is very scalable material, and it's CMOS compatible, and also it can be processed at a low temperature. Oxide semiconductor is also a good candidate for the back-end process transistor technology. So it has high mobility as a deposited channel material, and also it has a wide band gap, and which is tolerable for the high voltage application. And also it can be also processed by the low temperature. So by combining and integrating these components, then we should be able to build such a 1T, 1C non-volatile memory in the monolithic manner on top of the processing unit. So, however, the question is, so if we use such oxide semiconductor material, can we really drive such capacitor at high speed? And so that was my very simple question. So we simply estimated the kind of ferroelectric capacitor switching time as a function of mobility and also capacitor area. So this is a contour plot of the switching time of the ferroelectric capacitor at the relevant capacitor area compared to the DRAM capacitor. So I'm not going to detail how we draw this contour plot, but basically the key conclusion is if we have even though we have a 10 to 100 mobility range, which is lower than silicon transistor mobility, but we can find a certain design target to switch the such ferroelectric capacitor 1T1C memory cell less than 1 nanosecond region. So to target this region, in this work we design and fabricated and demonstrated the prototype of the back-end compatible 3D integration 1T1C capacitor and the transistor. So the objective of this work is, again, so to develop and integrate mobility enhanced FET and also good ferroelectric capacitor, and demonstrate 1T1C ferroelectric memory cell operation toward the 3D monolithic integration on top of the processor unit. And also we discussed the impact of the transistor characteristics on the 1T1C cell, and also investigate the physics of the mobility enhancement in our developed material. So, when we consider to integrate such oxide semiconductor transistor on the integrated circuit, the first one of the most important thing is the reliability. So, for the integrated circuit, reliability is very, very important. So we have to have a very robust transistor technology. So this graph compares previous reference IGZO-based transistors PBTI characteristics. And the right-hand side is our developed tin-doped IGZO transistor characteristics, PBTI characteristics. So as you can see, this tin-doped IGZO transistor has a much better PBTI characteristics with improvement. So we're going to use this tin-doped IGZO transistor for the following study. So here is the process flow of the 3D monolithic integration, and also this is a cross-sectional schematic of the demonstrated device structure. So basically, we started from the clean substrate and pass beta surface by SiO2. Then we fabricated a ferroelectric capacitor and also a tin-doped IGZO transistor on the same layer. So ferroelectric capacitors consists of bottom titanium nitride layer and ferroelectric hafnium oxide layer and tin-doped IGZO capping and a titanium nitride pad. So this is a ferroelectric capacitor. And we have a backgate type tin-doped IGZO channel FET with a titanium nitride bottom gate and titanium nitride source and drain. Okay, so this figure shows the top-down microscope image of the fabricated 1T1C memory cell. So this is a huge device because we fabricate in our university lab, but it's well made. So this is the IGZTO transistor, access transistor, and this is a crossbar type ferroelectric hafnium oxide capacitor cell. So it's connected to each other. And this graph shows the cross-sectional TM images of the transistor side and also capacitor side. For the transistor side, we can see that gate insulator hafnium oxide is amorphous, and the IGZTO channel is also amorphous. And the ferroelectric hafnium oxide capacitor side, so this is a ferroelectric hafnium oxide, and it's fully crystallized and uniformly. And IGZTO channel material is also kept amorphous. So the device is very well fabricated. So let me move on to the device readout and also have some discussion. So in this page, we compare typical drain transport characteristics of the reference IGZO transistor and then tin-doped IGZTO transistor. So as you can see, IGZTO transistor has a very well behaved transistor characteristics and a steep subthreshold characteristics. And this graph shows the output characteristics of the transistor. And then we compare IGZO transistor and the IGZTO transistor. And as you can see, output drive current is increased almost twice comparing to the reference IGZO transistor. And we also directly compare the channel mobility of IGZO transistor and the IGZTO transistor. So by incorporating the tin in this IGZO material, we were able to increase the channel mobility by 2 times. So to investigate the physical origin of this mobility enhancement, first we study the temperature dependence of the mobility for IGZTO transistor and the IGZO transistor. So so this is so we plot the mobility versus temperature, the inverse of temperature. So this is, and then we have a Arrhenius plot for each transistor mobility. And as you can see, the temperature dependence is much less in the IGZTO-FET compared to IGZO. So so this typically based on the transport theory of amorphous IGZO transistor, the transport characteristics is basically described by the so-called percolation transport. So this indicates that the difference in the percolation transport between IGZTO transistor and IGZO transistor. So the mobility can be described by the percolation transport theory and like this equation. So the mobility is proportional to the constant number times exponential of minus q phi over kBt. So phi is the kind of average potential barrier height in the amorphous semiconductor. So if you have a high potential barrier, in other words, high potential fluctuation in the amorphous material, you can have a low mobility. But if you can somehow lower this barrier height, and if you can have a smaller potential fluctuation, you can have a high mobility. So so the IGZTO channel seems to have the low potential fluctuation and low barrier height, and so that it has a high mobility. And to verify this discussion, we conducted the very preliminary ab initio calculations. So first, we made an amorphous model by using the melt and quench method by molecular dynamic simulation, and then we created a supercell for the amorphous semiconductor for both IGZO and also IGZTO. Then we calculated the kind of pseudo band structure for such amorphous unit cell, and we simulated roughly 10 samples for each cases. We chose randomly chose the 10 supercells for each cases, and simulated a pseudo band structure. And as you can see, comparing to IGZO, amorphous IGZO, a tin-doped IGZO channel has a much less potential fluctuation. So this is consistent with our discussion in the previous pages, which is the kind of low potential fluctuation in the amorphous IGZTO channel. So I think this is this smaller potential fluctuation is the kind of physical origin of the mobility enhancement in the tin-doped IGZO channel material. Next, we characterize the ferroelectric capacitor with IGZTO capping. From our previous study, if we have IGZO capping on top of the ferroelectric hafnium oxide, we can enlarge the ferroelectricity. So we already published this result by using the IGZO last year. So this time we apply the same technique for IGZTO capping. And again, we were able to obtain very high large ferroelectricity and very sharp switching characteristics. Moreover, previously we only demonstrated a 500 degrees C ferroelectric capacitor process, but this time we were able to demonstrate a 400 degrees C ferroelectric capacitor. So which is very promising for the back-end process compatibility, because the 400 degrees C is a kind of minimum temperature that can be applied for the back-end process. So we were able to achieve very fairly large ferroelectric charges and also very sharp switching with the IGZTO capping. And we also studied the reliability of this fabricated capacitor. So what's the most advantage with this IGZO capping or IGZTO capping is that we can achieve very stable endurance characteristics. So in the previous report, with the IGZO capping ferroelectric capacitor, we reported that the so-called wake-up-free, very stable endurance characteristics like this. So this time, we got almost the same results with IGZTO capping. As you can see, there's almost no unstable wake-up phenomenon with the IGZTO capping. So the endurance characteristics can be largely improved by the IGZO or IGZTO material capping. And next, now we're going to share the result of the 1T1C cell characteristics, memory cell characteristics. So we use the very simple pulse write scheme, and then we also use the pulse read scheme to read the 1T1C memory cell. And then for the cell current, we define our cell current by subtracting the non-switching current from the switching current, so that we can extract the kind of intrinsic ferroelectric polarization charge current. So this graph shows the right cell current characteristics and also read cell current characteristics as a function of different transistor gate bias. And as you can see, so please note that the write operation speed can be slower than read current, because in the write scheme, the transistor is something in the write situation, the access transistor operates like a source follow mode. So the operation speed is a little slower than the read operation. But nevertheless, as you increase the gate voltage, which is equivalent to the increase of the mobility, we can make the operation switching speed faster by driving the transistor by driving the transistor current further. And then and also we can see that for the read current, cell current is almost the same as the polarization switching current. So, which is good, because the cell current is only determined by the polarization switching characteristics. We also study the ferroelectric capacitor size dependence in this figure. So, and then as you can see, when you shrink the cell capacitor size, then we can make a faster switching compared to the larger cell capacitor. So these results basically consistent with our first estimation of the switching current in the first introduction page. So this is the final page for today's talk. So far we only showed our prototype 1T1C cell write characteristics and also read characteristics. But in the end, so we basically model our transistor and also ferroelectric capacitor in the SPICE. And by using this SPICE modeling, we predicted the switching characteristics for the very scaled 0.1 square micrometer ferroelectric capacitor and a DRAM-like FET access transistor DRAM-like size access transistor. So as you can see, by using these technologies, we should be able to achieve the sub 1 nanosecond switching with about 100 femtojoule per bit write and read energy. Let me summarize my presentation. So we developed the backend process compatible integration scheme of the FET access transistor and a ferroelectric capacitor using tin-doped IGZO material, IGZTO, and a demonstrated 1T1C ferroelectric memory operation toward the design target. And the mobility enhanced FET and the wake-up-free ferroelectric capacitor are obtained by using tin-doped IGZTO. The impact of thin film access transistor on 1T1C cell operation is studied, and the physics of mobility enhancement also is investigated. So we believe that the proposed technology of 3D monolithic integration will enable 3D embedded memory with high density and energy efficient computing. Thank you very much for your attention.